Hello everyone. The title of this video is Graph Radical Functions. And every question, every example I'm going to be doing in this video is taken directly from a free online textbook at openstax.org. It is their Intermediate Algebra 2nd edition text. And I'll be working on the exercises under the heading Graph Radical Functions. Now I'm only going to be working on the even numbered exercises, right, the ones that don't have solutions posted in the text. The odd numbered ones, you can click on the link on the question number, right, and it'll take you to the solution for that particular question. Right, so I'm just going to work on the even numbered ones, 384, 386, 388, and so on. I will also be putting timestamps for each example in the description of the video below. So example 1's timestamp will correspond to number 384, example 2 to number 386, and so on for all the even numbered problems up to number 404. All right. So you can bounce around, navigate the video more easily, hopefully, with the timestamps and see problems that you want to see more readily. All right, and then one last request I would have of you is that when I bring up a new question, pause the video and try to do it yourself first before watching me do it, right? And then compare. Right? Because if you're just watching me do these questions and not practicing yourself, chances are you're not learning all that much. Alright, so the first question is number 384. And in every single one of these questions, we are asked to A, find the domain of the function, right? What's allowed to be plugged in for the input variable, right? Which is going to be x for all these, right? So what's allowed to be plugged in for x. B, graph the function, right? So I'm going to make a rough hand graph, a graph by hand on some paper. It's not even going to be graph paper, right? And then I'll show you on the desmos.com, free online graphing calculator website. I'll show you a better picture of the graph. All right, and then we're going to use the graph to determine the range. Now remember, the range of a function was the set of the outputs, right? The domain is the set of the inputs. The range is the set of the outputs. For the domain, you're looking at the x-axis values that are used. And for the range, you're looking at the y-axis, right, the vertical axis values that are used in the graph. All right, so first question again is 384. I've got that written out here. So example 1, right, number 384. And once again, find the domain, graph the function, and then determine the range. Right. So we have f of x equals the square root of x minus 1. All right, so first the domain. Now, I have put up a video prior to this on finding the domain of a radical function. So hopefully you've seen that. If not, don't worry about it. We're going to do it again here. So notice this is an even root, right, square root. And if I want to talk about graphing these functions, right, the x-axis and y-axis represent real number lines, real numbers only. So I'd like real number inputs with real number outputs. Well, if I plug in a number that makes me take an even root of a negative number, that's not good. That's not real. And I won't be able to graph it. So the radicand, the expression inside the root, inside the square root, x minus 1, can't be negative. It has to be greater than or equal to 0. So for any even root function, I'm setting up this inequality. Odd root functions are easier. Right? For an odd root function, Usually the domain is just all real numbers. Then I solve this, right? We have x needs to be greater than or equal to 1. All right, so that's the domain. All right, the domain of this function is all values of x such that, x is greater than or equal to 1. Or, if you put this in interval notation, this will be 1 to infinity with a bracket on the 1, right, if you're asked to put it in interval notation. Alright, so now part 2 is graph the function. So once again, like I said, I'm going to make a rough hand sketch. Alright, so horizontal axis is x, vertical axis is, f or f of x, or just the y-axis, right? If you want to call it the y-axis, which is fine, that's standard. Now keep the domain in mind, because what I'm going to do is I'm going to make a little table of inputs and outputs, right? So we can get ordered pairs. So x and then f of x, or x then y, and we'll get nice ordered pairs that we can plot on our coordinate plane. So notice the only values I'm allowed to plug in are 1 or greater. So I'm going to start with 1. I'm going to start with 1 and then just start plugging in bigger values of x. Now I'm going to pick them strategically though. This is a square root. So I'm going to pick values of x that will give me a perfect square inside, to make it easier to do. You'll see what I mean. So 1, now if I plug in 1, this is going to give me the square root of 0, which is 0. Right? So 1 comma 0. So say here's 1, and I'll plot that point. Right? Here's a 1 comma 0, which would just be on the x-axis. Right? There we go. 1, 0. Now if you plug in 2, that's good too. Right? If I plug in 2, you'd have the square root of 1, which is just 1. Right? So 2 comma 1. So 2 on the x, 1 on the y, and there's that point. Now you can plug in 3 if you want, but if I plug in 3, that's going to give me the square root of 2, which is about 1.414 something. And I mean, you can do it, nothing wrong with that. It's just I'm gonna pick values of x that give me a perfect square inside. So we had 0 in there, we had 1 in there. Next thing I would want is 4, right? 4 is 2 squared. So x would need to be 5 for that to happen, right? If x were 5, you'd have the square root of 4, which is 2. So input 5, output 2. Alright, and then the next perfect square would be 9, right? 3 squared. Well, x would need to be 10 for that to happen. Right? So input 10, output 3. Right? Square root of 9. 6, 7, 8, 9, 10. And this is about as far as I'm going to go here in my drawing. Output 3. And there's that point, 10 comma 3. Now, again, this is a hand drawing. This isn't perfect. But what you're going to notice about these square root functions is that their graphs look like like the top half of a parabola. Remember, parabolas are like U-shaped. Well, this is just half of it, right, in the top half. And this will go up forever, right? This is going to keep going up. If I could keep increasing the output, right? If I plugged in 17, you'd get 4. If you plugged in 26, you'd get 5. If you plugged in 37, you'd get 6. Right? So like that's going way out to the right. X equals 26, 37, way out to the right. But notice the value of the function keeps going up. 0, 1, 2, 3, 4, 5, 6. I could have it go up as high as I wish. It's just going up very slowly. Right. So there's the graph. And we got the domain, from 1 to infinity, x is greater than or equal to 1. We have a graph here, a nice hand drawing, which I'll show you a better Desmos drawing in a second, a better graphing calculator drawing. And then the range. Now the range you can write as, y values. I'll say all y such that, just now you're looking at the vertical axis. What y coordinates are being used? Well, notice that none of these points on the graph have negative y values. In fact, the first point I plotted here at 1, 0, that's the lowest y value. So 0 and greater, right? All these points on the graph have y values of 0 or greater. So y is greater than or equal to 0. You could write it in set builder notation like this, or in interval notation, right? Talking 0 and up, from 0 to infinity, looking at the y-axis values again, with a bracket on 0, right? 0 is included, right? 0 is the y-coordinate of this point here. 0 is an output. Right, maybe I should circle some of this stuff, right? So the domain we got, the graph, and the range we got. All right, now let me actually go to that, again, that desmos.com website. Here it is, desmos.com, free online graphing calculator, and enter the function we were given, right? F of x equals the square root of x minus 1. And you see that picture, see it's got 1, 0, 2, 1, 2, 1, right? 5, 2, there it is, whatever. But I can put all sorts of points on here. And you see how as you move to the right, the graph just keeps going up and up and up, right? The y coordinates keep getting bigger. So the y coordinates are, the lowest one is again y coordinate of 0, and then up, 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 up forever, right? So from 0 to infinity would be the range. And the x coordinates go from 1, and then those, x coordinates get bigger and bigger as well, right? So from 1 to infinity for the domain. Okay, wonderful. All right, so I'm going to keep coming back here and checking to see if our hand drawing matches the Desmos drawing. Let me go back to Desmos. All right. Okay, great. All right, so next question. Same instructions, right? Find the domain, graph it, and then use the graph to state the range. All right, so this is pretty similar actually. Number 2 is exercise 386 in the text. Another square root function. We have g of x equals the square root, and the radicand is x minus 4, right? The square root of x minus 4. All right, so first the domain. Now it's another even root, right? So the expression inside the root, right, x minus 4, needs to be greater than or equal to 0. Right? It can't be negative. And just simply adding 4 here, we would see that x has to be greater than or equal to 4. And there's the domain, right? So the domain of this function is all values of x such that x is greater than or equal to 4. Or if you're putting this in interval notation, that would be from 4 to infinity, right, with 4 included. Right. So there's the domain, right? X is greater than or equal to 4. And now I'll make a graph, right? Again, I'm just going to do a simple hand drawing here. X-axis, y-axis. You could also call the outputs g of x, right, instead of y. Same thing. And I'm going to make a table, just like before, with inputs and outputs, x and g of x, or x and y. But I have to start it at 4, right? I can't plug in anything less than 4. Now if I plug in 4, that's going to give me the square root of 0. Cool. If I plug in 5, that'll give me the square root of 1, which is 1. And I'll start plotting points, and I'll make these tinier. 1, 2, 3, there's 4, 5, right? And then, so we have 4 comma 0, 5 comma 1. And just start plotting points over here. 6 would give me the square root of 2, 7 would give me the square root of 3, which again, you can plot those if you want. It's just that the square root of 2 and square root of 3 are not so nice. Right? 8 would give me the square root of 4, so 8, 2. Right? Square root of 4 is 2, so 8, 2. So input 8, output 2. Let's plot that point. Then 9 would give me the square root of 5, which isn't nice, but still you could do it. 10 would give me the square root of 6. 11 would be the square root of 7. 12 would be the square root of 8. 13 would give me the square root of 9, which is 3, right? So input 13, and you'd get an output of 3. So 8, 9, 10, 11, 12, 13. Output of 3. And I can keep going with this. It's just, there's only so much room on my paper here. But, connecting the dots. Again, it's like, all these square root functions are going to look like half a parabola, opening to the right or to the left, depending on which way the thing goes. So it's like this. Right? Starting from the point 4, 0, and then moving up and up and up and up to the right. And like I said, in the last example, this goes up forever. It doesn't just stop at a y value of 3. If I plugged in 18, I'd get 4. Because that'd be the square. No, if I plugged in 20, sorry, I'd get 4. If I plugged in 18, it'd be the square root of 14. If I plug in 20, I'd get 4, right? Square root of 16. And if I plugged in 29, I'd get 5 as an output, right? Square root of 25, and so on. But I could make the output as large as I want, but it'll never be less than 0, right? So there's the graph. Right. Cool. And then from the graph, we determine the range, which again, I'll just say it's all y values such that, and looking at the points of the graph, and then the y-axis, what numbers do they line up with on the y-axis? Well, the lowest y value used is 0, and then it just keeps going up, right? So y is greater than or equal to 0 again, which in interval notation would be from 0 to infinity, right? From 0 to infinity, bracket on 0, right? Parentheses on infinity. There's the range. All right, and then once again, let's take a look and just make sure that our graph by hand here kind of matches what the actual graph should look like, right? A better graph on a calculator. So I'll enter it the way they gave it to me. G of x equals the square root of, and then you had x minus 4 all inside. And yeah, you see this point 4, 0 is where it's starting, and then it goes up and to the right, kind of this, again, this like half parabola going this way. Looks good. All right, looks good. Looks like what I drew. All right, excellent. Okay, next question. Now the next question is another square root, but this time, there's this minus 2 is not inside the radical, it's outside, right? And that has an effect. That'll have an effect on the range, right? So far, the range has been 0 or greater, right? Y values 0 or greater, but having something outside the square root, like this minus 2, will affect the range, as you'll see here. All right, so number 3, exercise 388, we have f of x equals the square root of just x, and then minus 2. Still a square root though, still an even root, so x needs to be greater than or equal to 0, right? Whatever the radicand is needs to be non-negative, and that's already solved for. All right, so the domain is all values of x such that x is greater than or equal to 0. All right, and then in interval notation, right, x is 0 or greater, that's from 0 to infinity, right, including 0 though, so a bracket on 0. All right, so here's the domain, right, the values I can plug in for x. Then we're going to make a graph, right, and again I'm going to do just a rough hand sketch over here. X-axis horizontal, the y-axis, or you could call it f of x, the f-axis being the vertical axis. And I'm going to make a table, right, with inputs and outputs and plot these ordered pairs. So x and f of x, or x and y, whatever you want. Now I have to start it at 0, right? The only values I'm allowed to plug in are 0 or greater. So if I plug in 0, the square root of 0 is 0, but then you have this minus 2. So the output would be negative 2. Right, so 0 for x, and then negative 2 for y. So starting here, 0, negative 2. Then once again, it's a square root. So I'm going to pick values of x strategically so that we have square roots of perfect squares. Now, if x were 1, that's good. The square root of 1 is 1. But then you got minus 2. 1 minus 2 is negative 1. So I have the ordered pair 1, negative 1. So input 1, output negative 1. And that would be this point here. All right, then you can plug in 2, and you have the square root of 2, then minus 2, which is fine. I mean, that is a number. You can plot it. It's just not a nice number. Square root of 3, now square root of 4. Right? Plug in 4 for x, and you get 2, but then minus 2 would be 0. All right, so 4 comma 0. So input 4, output 0. And then 5, 6, 7, 8, 9. Plug in 9. Square root of 9 is 3, but then minus 2 would be 1. So input 9, output 1. All right, and you see it's very similar to the other square root functions I've been drawing for questions 1 and 2. It's just this kind of a half parabola thing again, opening this way, going up forever, starting at the point 0, negative 2, and going up and up and up and up and up as I go to the right. So here's, I'm not going to circle the graphs anymore, it's kind of too busy. So here's my graph. And then once you have the graph written out, right, you should be able to state the range pretty easily, right? So the range is all y values. But this time, looking at all the points on this graph and seeing what y coordinates they line up with, right, the lowest one is at negative 2 this time, not at 0. So we're going negative 2 and up, right? Every value from negative 2 and up on the y-axis is used in this graph. So y is greater than or equal to negative 2. Or if you want to put this in interval notation, that would be from negative 2 to positive infinity, right? Negative 2 to infinity, including negative 2, right? A bracket on negative 2. And there's your range. And then again, just to test it out, let's punch this in my graphing calculator, right? The Desmos site. I'll just punch it in as it looked, f of x equals the square root of x, and then get out of there, and then put the minus 2, right? Don't put the minus 2 inside the square root of x, it's outside. And look, see? 0, negative 2 starting, and then moving up and up. 4, 0, we said 4 comma 0 was on there, right? And all those other points from my table, and it just keeps going up and up and up as you move to the right. Fantastic. And again, looks like that kind of a half a parabola opening to the right. Wonderful. Okay. Next question. All right. Still a square root involved here. Number 4, which is exercise 390. we have g of x equals, 3 times the square root of x. So you still have the square root of x, but then you have this, times 3 afterwards. So that's going to affect the outputs. All right, so let's see. Now the domain is no problem, right? Again, just look inside an even root, the square root here. This radicand x can't be negative, right? So x has to be greater than or equal to 0, and that's it. That's already solved for. So the domain of this function is, all x such that x is, greater than or equal to 0. Or, again, the bracket around 0 to infinity, if you're putting it in interval notation. So there's your domain. All right, then we'll make a graph. X-axis, y-axis, or g-axis if you want to call it the g-axis. That wouldn't be wrong. And then I'm making a little table here with inputs x and then outputs g of x or y. Domain tells me, I can only plug in values 0 or greater, so I'm going to start with 0. Now, the square root of 0 is 0, but then I have to times 3, which is still 0. So I got the origin. 0, 0 is where this graph is starting. Then square root of 1 is 1, times 3 is 3. So input 1, output 3. 1, 3. Alright, and 3 times the square root of 2, when the input's 2. When the input's 3, it would be 3 times the square root of 3, which again isn't nice. You could still do it, but it's not nice. And then put in 4, right? You get the square root of 4 is 2, but then times 3 is 6. Right? So input 4, output 6. So 4, 6. Now I'll just do one more here. Put in 9. Right, square root of 9 is 3. 3 times 3 is 9. Input 9, output 9. Output 9. Again, I'm doing a eyeball in this. This isn't perfect. But once again, you see this kind of half parabola shape. It's just a little steeper. The increase is faster because of the times 3. The increase, it is increasing faster than those previous graphs I was making. And again, that's because of the multiplication by 3. And it's going to be going up forever, right? If I plugged in 16, I'd get 12, and if I plug in 25, I'd get 15, right? And there we go. There's our graph. Now, once you have the graph down, we can state the range, right? The range, just looking at the y-axis, right, the vertical axis, it's all the y values that are 0 or greater, right? We're starting down here at y equals 0, and then all the points here keep, the y value just keeps going up and up and up. So y is greater than or equal to 0. Or in interval notation, once again, from 0 to infinity with a bracket on the 0. So there's our range. All right, and then let's take a look at this graph on Desmos. So we have g of x equals 3 times the square root of x. Right, and there it is. Right? And yeah, see, starts at 0, 0 and just shoots up. You see you got 1, 3 here, right? 1, 3, and all those points I said that I plotted by hand. And it just, increases very quick, much more quickly, 3 times as fast as the other one did. Okay, great, looks good. All right, next question. Another square root. We'll eventually get to ones that are have cube roots or whatever. But another square root. So number 5, exercise 392 in the text. F of x equals the square root of 4 minus x. Right now, 4 minus x is all inside the square root. So that 4 minus x can't be negative, right? It's got to be greater than or equal to 0. And then solving this for x would give me x is less than or equal to 4. All right, x has to be less than or equal to 4. So here the domain is, all x such that x is less than or equal to 4. Now, if you put that in interval notation, that's from negative infinity up to 4, right? With a bracket on 4. Right, all the values less than 4 or equal to 4. So there's the domain. Alright, then we'll make a graph. I'm going to do x-axis, y-axis again over here. Or x-axis and f-axis, right? The function's called f, output's called f of x. Alright, then I'll start making a table, like always. X and f of x. Starting at 4. And then go left, right? We have to do 4 or less. So input 4, right, 4 on the x-axis, output 0, right? We have the square root of 0. So I'll plot that point. Input 4, output 0. There we go. Now I can't plug in 5 or 6 or 7. Again, we have to go left here. We have to plug in values 4 or less. And I'm going to pick values of x so that I get perfect squares in here. So 3, right? If x were 3, 4 minus 3 is 1, square root of 1 is 1. Right? So input 3, output 1. Alright. Then input 0, right? 4 minus 0 would be output 2, square root of 4. Right, so 0, 2. Input 0, output 2. Okay, now we're getting into negative inputs, right? If I plug in negative 5, 4 minus negative 5 would be 4 plus 5. That'd be 9. Square root of 9 is 3. You get input negative 5. There's negative 5. Output 3. Alright, now I'm going to call it there. You can keep going though, but you got to keep going left. And you see it starts here at 4 comma 0. And it's like, again, it's another square root function, so it's another kind of like a half a parabola, but this time opening to the left. Right, so it's going up forever, but to the left. Right. So there's the graph. And then once the graph is in, we can easily state the range. So again, range is y values. And once again, if you look at the y-axis, this graph starts at y equals 0 and goes up. Right? So from y is greater than or equal to 0 again, or from 0 upward, from 0 to infinity in interval notation with the bracket on 0. Okay. And then once again, I'll enter this function on the Desmos site, and we'll take a better look at it. Right? A much cleaner looking graph. We have f of x equals the square root of 4 minus x. And look at that. See, it's that half parabola opening, starting at 4, 0 here, and then curling out to the left. All right, and see there's 0, 2. We said 0, 2 was on this as well, right? That was part of my table. Good, so looks good. Looks like my drawing wasn't that bad. Great. All right, next question. So we got another, I think this is the last square root question that I'm going to be doing. So again, there's number 6, number 394 in the text. G of x equals, so see this negative outside the square root, right? Negative 1 times the square root of x, and then you have plus 1 still outside. Right, the only thing inside the square root is x. So x has to be greater than or equal to 0. Right? Can't take even roots of negative numbers. So that's the domain. Right? So the domain is all values of x that are greater than or equal to 0. In interval notation, you've seen this a bunch now. That's from 0 to infinity, but including 0. All right, so I got the domain. Can only plug in values 0 or greater. Now let's try graphing. All right, so when I make my table, x and g of x, or x and y, starting at 0 for my input, right? And then I move to the right, right, 0 or greater. Now when I plug in 0, you get the square root of 0, which is 0. Then you got to multiply by negative 1, and then add 1. So 0 times negative 1 is still 0, plus 1 would be 1. Right, so input 0, output 1. So there's that point. Okay, then again we have square root of x, so just plug in 1 next. That's a perfect square. Square root of 1 is 1, times negative 1 would be negative 1, plus 1 would be 0. So I have input 1, output 0. So that's on the x-axis, right, the x-intercept. So it looks like this one's going to be curving down, going down forever. And that has to do with the fact that we multiply by the square root by a negative number. Alright, then the square root of 4 would be nice, right? If x were 4, the square root of 4 is 2. So this is negative 2 plus 1 would be negative 1 for the output. So input 4, output negative 1. So that point there. Then I'll plug in 9, right? Square root of 9 is nice. So you'd have negative 3, right? Square root of 9 is 3. Negative 3 plus 1 would be negative 2. So input 9. Input 9, output negative 2. And you see that this graph is going down forever. Right? The value of the function, the y values, are decreasing. Still this half parabola shape, right, starting at the point 0, 1 here, and just going down forever, just this half parabola shape. Make it a little more smooth here. Okay, great. Alright, so now that I have the graph in, we can state the range. Again, it's all y values. Now this time though, looking at the y-axis, what outputs are used in this graph. The highest value of y is 1, and then it just goes down. So y is all y are used such that y is less than or equal to 1. Right, 1 or less for the y coordinates. And in interval notation, that would be from always go low to high. That'd be from negative infinity up to 1. So negative infinity comma 1 here with a bracket on the 1, right? 1 is a y coordinate at that point 0, 1. So there's the range, right? Y is less than or equal to 1, or from negative infinity to positive 1 on the y-axis. All right, and then once again I'll look at this, maybe look at a better picture on the graphing calculator, right? Desmos. This was g of x equals negative square root of x, and then after that, get out of there, plus 1. All right, and look at that. All right, perfect. All right, you got 0, 1, like I said, would be on there, 1, 0, and it's this half parabola shape, but going down, right? Opening down and going down to the right. Looks good. Looks like I made a decent hand drawing. Okay. Next question. Now we have a cube root. So this is number 7. Exercise 396. F of x equals the cube root of x minus 1. Odd root. Remember, you can take odd roots of positive numbers, negative numbers, 0, any real number. So as long as there aren't denominators with variables, any odd root function, the domain is all real numbers. I'm just going to put that the interval notation for all real numbers. Now you can write out the words all real numbers if you want, but this is a little quicker. So there's the domain. You can plug in anything for x. Anything. So makes the table a little trickier. So I'm going to go in to try and graph this thing. Now when I make the table, here's what I'm going to do. X and f of x here. We're trying to find, this is a cube root, so I want to plug in values of x that will give me a perfect cube in the radicand. Now remember, there are positive perfect cubes and there are also negative perfect cubes, so I'm going to go in both directions. So I'll start with 0. If I plug in 1 for x, and I'll put it in the middle here, you'll see why in a second. If I plug in 1 for x, that'll give me the cube root of 0, which is 0. 0 is a perfect cube. So input 1, output 0. So there, that point there. Alright, now, I'm going to start going to the right first. Get my positive cubes. Now, 1 is a positive cube, 1 is 1 cube, so if I plug in 2 for x, that'll give me the cube root of 1, which is 1. So input 2, output 1. Eight is a perfect cube. Well, to get 8 inside the cube root, I need to plug in 9 for x. Plug in 9 for x, you get the cube root of 8, which is 2. Now you could plug in other numbers, it's just the outputs won't be as nice. So input 9, output 2. 9, 2. There. And if you notice, that'll keep going, that'll keep increasing, going this way, starting from 1, 0 here. And this will just keep increasing, just very, very slowly. To get to an output of 3, the cube root of 27 is 3. I'd have to plug in 28 for x to get an output of 3, and I'm not going out to 28 on the x-axis in this drawing. And you could just, again, keep going, get the outputs to go up and up and up and up, going that way. But that's not all. This is just like half the graph. We can go to the left as well. You can take cube roots of negative numbers. Now the negative cubes would be negative 1. Now to get negative 1 in here, I'd have to plug in 0 for x. Right, if I plug in 0 for x, that's the cube root of negative 1, which is just negative 1. So 0 input, negative 1 output. That point there. And then, negative 8 would be a perfect cube, negative 2 cubed. To get negative 8 inside the cube root symbol, I need negative 7 for x, right? Plug in negative 7 for x. And the cube root of negative 8 is negative 2. Right, so negative 7 for x. This isn't perfect. And then, negative 2 for the output. So negative 7 input, negative 2 output. There we go. And once again, as I go left here, this will go down forever. Negative 1, negative 2. I can get to negative 3 and negative 4 for y. If I want to get negative 3 as the output, I need to put in negative 26. Right, so at negative 26 input, I'd have negative 3 output, but it would be going down forever. So again, starting at this 1, 0 in the middle here, it would just be doing this, right? Going down forever that way. And every cube root function will look like this, kind of like a very stretched out S shape. I mean, this is a very elongated S shape. All right. But every cube root function will have this kind of a shape. Now it's either going to be an S that way or a backwards S, but it'll have some sort of stretched, elongated S shape. And then once the graph is put up, right, the range can be stated. And just like for the domain, the range is very simple for odd roots as well. Notice how, output, y value of 0, and then going this way, we get all the positive y values. Going this way, we get all the negative y values. So the range for these odd root functions, cube root, fifth root, and so on, is also all real numbers. So I'm just going to write the interval notation for that again. So yeah, and this is going to be the same for any of the odd root functions, cube root, fifth root, seventh. The domain's all real numbers. The range is all real numbers. Great. All right, let me put this in the calculator, the graphing calculator Desmos site. Right? We have f of x equals. Now, if you want to put in the cube root symbol, you got to bring up the keypad, go into functions, and then miscellaneous functions. Got the nth root thing here, and then you enter 3 for the index for the cube root. I got cube root of x minus 1. And look at that. See, it's exactly the same as I drew. A little curvier than what I drew. But you see you got the point 1, 0 there. You got the point 0, negative 1 as I had. You got the point 2, 1. Right, 2, 1 like I had, and so on, right? And again, you stretch it out here, you see how, if I start from the point 1, 0 and go to the right, it's just going up forever. Start at the point 1, 0 and go left, it's just going down forever, just very slowly. But the range would be all real numbers, right? Domains are all real numbers, range is all real numbers, and it's one of these elongated S-looking shapes. Okay, wonderful. So my hand drawing didn't look that much different than this. So not bad. Great. All right, the next one's very, very similar. It's another cube root. But instead of the cube root of x minus 1, it's the cube root of x minus 2. So things are just going to get shifted over 1 unit, you'll see, from number 7. So number 8, which is exercise 398, we got g of x equals the cube root of x minus 2. Again, it's a cube root, odd root. So the domain is all real numbers. All right, the only time it wouldn't be all real numbers with an odd root is if there was a fraction, where there was a denominator that could be 0, but there are no denominators that could be 0 here. So once again, the domain is all real numbers. You can plug in whatever you want for x. All right, then I'll make a graph. Start making a table. This is x and g of x. And then once again, in the middle of it, I'm going to put in whatever gives me the cube root of 0. All right, so that'd be 2. X equals 2 would give me the cube root of 0, which would be 0. All right, so input 2, output 0. And then I'll start going to the right first, and then I'll go left. So if I plug in 3, we'll have the cube root of 1, which is 1. And I'll put the ordered pairs first, then I'll plot them. The cube root of 8, I'd have to plug in 10 for x for that, right? If I plug in 10, we have the cube root of 8, which is 2. If I plugged in 29, I'd get 3, right? The cube root of 27, and so on. So we have input 3, output 1, and input 10, output 2, right? And again, I'm not going to go out to 29 here. Right? So 3, 1, 10, 2, and the graph will look like this to the right of the point 2, 0. It'll just be increasing like this, going up forever. And this, it's more curvy than that. It's more curvy than this, but so like that, right? And increasing, going up as high as you want it to be. But I can go left as well, right? It's an odd root. You can take odd roots of negative numbers. All right, so if I plugged in 1 for x, I'd get the cube root of negative 1, which is negative 1. Right? So input 1, output negative 1. And if I plug in negative 6 for x, I'd get the cube root of negative 8, which is negative 2. And if I plugged in negative 25 for x, I'd get the cube root of negative 27, which is negative 3. All right, I'm just doing nice whole ones. You can plug in other numbers too, right? If I plugged in 0, we'd get the cube root of negative 2, which is, you can plot that, but it's just not nice. So 1, negative 1, and then negative 6. Negative 6 input, negative 2 output. Plotting these points. So 1, negative 1. Negative 6, negative 2. And again, I'm not going to go out to negative 25 to get to negative 3, but you see that if I start at 2, 0 here and go left, we got this function that's going down forever this way, right? And yet again, once again, it's one of these elongated S shapes. Right? All the cube root functions will look like that in some way. Whether it's a regular S or a backwards S, doesn't matter. Alright, so then, once again, the range is all real numbers, right? It's going up forever, down forever. Every single y value is in some ordered pair. Alright, so the range is all real numbers as well. Very easy for these odd roots. Alright, let's take a look. Alright, so I'll enter the function as it was given to me, right? G of x equals, and then you can find the cube root symbol if you want, but I'll just put the radicand, which was x minus 2, and raise it to the 1/3 power. Remember, raising to the 1/3 power would be the cube root. And here you go, right? You see 2, 0. Now 0, cube root of negative 2, negative 1.26. But, it's got all the points that we had, 3, 1, right? 3, 1 said would be on there. 1, negative 1. Right, 1, negative 1. All the points that I said would be on there on my hand drawing are on there. And you can see if I zoom out, right, the domain's all real numbers clearly. And if I go from 2, 0 to the left, you're going down forever. If I, so I get all the negative outputs, negative y values. If I go from 2, 0 to the right, I'm going up forever, so I get all the positive y values. So, the range is all real numbers as well. Right, and that doesn't, it looks a little curvier, a little sharper here in the middle than my hand drawing, but the hand drawing is not that bad compared to this. All right, great. All right, so number 9. All right, next question. I have another cube root. All right, but this time the radicand is just x. All right, this minus 3 is outside the radical. All right, so it's the cube root of x, then minus 3. All right. But still the domain is all real numbers. All right, there are no denominators that can be 0 here, and it's an odd root. You can take the odd root of any number. So the domain is once again all real numbers. And you're going to see the range is also going to be all real numbers. But let me make a graph. Yeah. All right, and instead of making the table like I've been making, I'm just going to plug in the numbers put the numbers in on the thing. If I input 0, right, cube root of 0 is 0, then minus 3, output negative 3. All right, so input 0, output negative 3. And then I'll start going to the right. Input 1, and then 1 minus 3 would be, the cube root of 1 is 1, 1 minus 3 is negative 2. So input 1, output negative 2. And then if I put in 8, the cube root of 8 is 2. 2 minus 3 is negative 1. So input 8, output negative 1. And if I put in 27, I'd get 0, 3 minus 3. But yeah, so like starting from this point 0, negative 3, and going to the right, the graph is going up forever, but very slowly, right? It would eventually hit any value you wish above negative 3. Then going to the left, if I plugged in negative 1, right, cube root of negative 1 is negative 1, minus 3 is negative 4. And so input negative 1, output negative 4. And then input negative 8, output negative 5. Right. So input negative 8, cube root of negative 8 is negative 2, minus 3 is negative 5, right? Output negative 5, and there you go there. All right, and so if you start at this point, 0, negative 3, and go left on this graph, it's going down forever, right? Just very slowly. And again, we have one of these elongated S shapes for a cube root function. And the range is all real numbers also, right? It's going up forever that way, down forever that way. Every single y value would eventually be used, right? So the range is all real numbers also. Very, very simple for odd roots. All right, let's take a look. See if our graph, my hand graph matches the calculator graph pretty well. So here it was f of x equals, the cube root of x, or just x to the 1/3 power. And then after that, minus 3. And yeah, that totally matches what I have, right? Here's 0, negative 3, 1, negative 2. 1, negative 2 should be on there. Well, you can plot, there you go. All right. And all the other points I stated. And again, you zoom out, you're going to see it, it's going up forever to the right, going down forever to the left, just very, very slowly. So every single y coordinate, every single value on the y-axis is used as a y coordinate at some point in this graph. So the range is all real numbers as well. Fantastic. All right, next question. So another cube root function. Very similar. This one's pretty simple. The only difference between this and the previous ones is, so far we've been seeing these S shapes like this, right? This one is going to be the backwards S. It's going to be like that, right? You'll see. Just ignore this for now. Right? Don't worry about that. All right, so it's another cube root. G of x equals, negative 1 times the cube root of x. Domain's all real numbers. You can plug in anything to a cube root. Right. So again, very, very simple. Again, I'll make the graph, but without, I'm not going to make the chart this time again. Right. Cube root of 0 is 0. So I got 0, 0. Right. The origin is on this graph. The cube root of 1, or if I plug in 1 for x, the cube root of 1 is 1, but then we're multiplying it by negative 1. So the output would be negative 1. Input 1, output negative 1. Then if I plug in 8, well, the cube root of 8, that's good. Right? That's a perfect cube. And if I plug that in, cube root of 8 is 2, but then don't forget this minus 1 here, so the output would be negative 2. So input 8, output negative 2. And do you see that if I start from the origin here and go to the right, we're going down forever. Just very slowly, right? But that's going down forever. All right, then if we go to the left, if I plug in negative 1, cube root of negative 1 is negative 1, but then times negative 1 again would be positive 1. Right? Yep. Input negative 1, output positive 1. And then if I plug in negative 8, I'd get a perfect cube, right? Yeah. Plug in negative 8. The cube root of negative 8 is negative 2 times negative 1 would be positive 2. So input negative 8, output positive 2, right there. And hopefully you can see that starting from the origin again, if I go to the left, it's going up forever. But just very slowly, right? And so going up forever that way, down forever that way. There's a graph, and again, it's this back. It's like again an elongated S shape, but just a backwards S. Right? And the range is once again all real numbers. Right? Very simple with the odd roots yet again. Okay, and let's take a look at this on the calculator, right, the Desmos site, and see that our hand drawing, pretty well matches what they have. Right? All right, so this was g of x equals negative, and then x to the 1/3 power. Right? Negative 1 times x to the 1/3 power, and you see this, this exactly what I had on my drawing. Right? You got 0, 0 there. You got 1, negative 1. You can plot the point. 1, negative 1, 1 comma negative 1. There it is, right? That's on the graph. And other points that I found. And if you zoom out, you see again, it's going up to the left forever and down to the right forever, just very, very slowly, right? So the range is indeed all real numbers as well as the domain. Great. All right, and I got just one more of these. So here it's f of x, so number 11, exercise 404 in the text. F of x equals negative 2 this time, not negative 1, just negative 2 times the cube root of x. So very similar to the last question, but instead of multiplying by negative 1, we're multiplying by negative 2. So again, the domain, it's an odd root. Domain is all real numbers, and there are no denominators that could possibly be 0. Right, so from negative infinity to infinity. Right, so again, the domain is all real numbers. Just going to make the graph real quick. Not going to make a table again this time because it's pretty easy to tell what we should be plugging in here. Now the cube root of 0 is 0. 0 times negative 2 is negative 2. So, I'm sorry, 0 times negative 2 is 0. So 0, 0. Right? Input 0, output 0. So the origin would be on this graph. Then plug in 1. Let's go to the right. Cube root of 1 is 1, but then times negative 2 would be negative 2. Right, so input 1, output negative 2. Then the cube root of 8 is nice, right? So plug in 8 for x again. And input 8, and then the cube root of 8 is 2, times negative 2 would be negative 4. Right, so the only thing that multiplying by negative 2 does is it makes it decrease just a little more quickly as I go to the right here, right? 8, negative 4. And if I plugged in 27, it would be at negative 6, and so on. Right? So it just makes it decrease a little more quickly as I go to the right. Like that. But that's just going to the right of the origin. Go to the left, if I plugged in negative 1, cube root of negative 1 is negative 1, but then times negative 2 would be positive 2. Right? Input negative 1, output positive 2. And then I input negative 8, right? The cube root of negative 8 is nice. Input negative 8, output would be positive 4. Because the cube root of negative 8 is negative 2, but then times negative 2 would be positive 4. And you see if I start from the origin and go left, it's going up forever. And it's going up a little more quickly than usual because of this factor of 2. Right? But yeah, so again, cube root, still one of these elongated S shapes. Right? And the range is, again, hopefully it's clear that the range is all real numbers, right? It's going up forever, down forever. Every single y value would be used in some point on this graph, right? So the range is also all real numbers yet again. All right, so square roots are a little trickier. Right? Square root, remember you can only take the domain of a non-negative number, so that restricts the domain. And then depending on where the square root function starts will determine your range, right? And it's going to start at one point and move either up or down. But the cube root functions, no problem, right? You can go to the left, go to the right forever, go up and down forever. You know, they do it in some way, so the domain and range is always, you know, all real numbers for these. Wonderful. All right, and let's punch this in one more time. See if our little hand drawing here matches the actual graph. Right? F of x equals -2 times x to the 1/3 power, right, times the cube root of x, and indeed it does. Look at this. Got the origin. Right, you got 1, -2 is on there. -1, +2 is on there, and so on. Right? See, 8, -4 is on there. -8, +4 is on there, as I was pointing out with my hand drawing. Looks good. And if you zoom out, right, it's going up forever that way, going down forever that way, so hopefully it's clear that the range is all real numbers. Wonderful, wonderful. Okay, and that's it. All right. So I'm hoping that watching me go through these 11 questions here, help you in some way when you're asked to graph radical functions, especially square roots and cube root functions on your own. And thank you very much for watching.